Hi, in this video, let us take an intuitive approach to understanding the concept of limit of a sequence. So let's look at what I have here. I have here guess the limit of the sequence 1 over n, and since we are taking an intuitive approach, our intuition will be developed from numerical methods as follows. So here this sequence 1 over n, if we expand it out, this is the sequence we have in mind. Remember, n is an element of the natural numbers. So to get the elements of the sequence, we put n equals 1 to get the first element of the sequence, n equals 2, that gives us the second element of the sequence, and so on, and that's how we get them. And we're looking at the sequence and think about plotting them on the number line. As you can see, 1 over 1, that would be that point. If you plot the second number of the sequence, I won't plot it here, but it will be somewhere here, exactly in between 0 and 1. 1/3, that is 1/3 of the way, probably somewhere here. And as you can see intuitively, that when you begin to plot these numbers, those numbers are getting closer and closer and closer to 0. In fact, you could also make a table where you don't really have to write all of the elements of the sequence. You can simply look at the 1000th element of the sequence if you like, compute 1 over n, and you can look at a pattern in these numbers. You can see these numbers are getting smaller and smaller positive numbers. So in fact, our intuitive idea is these numbers are getting closer to 0, and in math the correct vocabulary is the limit of the sequence is 0, and this is the notation for it. This is the sequence. This is in fact the formula for the nth term of the sequence, 1 over n. LIM stands for limit, and we write n goes to infinity because look at this, in the sequence we have, and this is an infinite sequence because remember we thought of sequences as functions where the domain is the natural set of natural numbers. So for n we get to put in 1, 2, 3, 4 and so on, and as you know the natural numbers go on forever, and so because of that this is an infinite sequence, and we are asking, as we plot all of these points, it's an infinite number of points on the number line, do we see a pattern? And we just said yes, we do. We think those numbers are getting closer to 0. So that is this n goes to infinity indicates that we're looking at the sequence down the lane all as we go down. So learn this vocabulary. For now, if you get this much in this example, that's pretty good. So even though we should move on to another numerical example, I want to dig just a little deeper for a few minutes, even if you don't understand everything in here. So I want to talk about what does it mean to say that these numbers are getting closer to 0. Remember, math is very precise and we have to understand what closer means. And I'll give you still an intuitive approach to understanding this closer, what closer means. In another video, I'll give you a precise definition. So for now, think that we're going to specify it by drawing an open interval like that. Sometimes we call it a neighborhood of 0. That is a math word, neighborhood. We can also call it this interval neighborhood of 0. So what it so let's say that's what I mean by close to 0, if any number lies in this interval. So as you can see, the first element of the sequence, it does not lie in this neighborhood of 0, and 1/2 is somewhere here. It does not lie in this interval. But you will pretty soon realize if we start plotting these points, they will be a cutoff point where you will be able to say, okay, the first few numbers, finite number of numbers in the sequence, maybe they don't lie within this interval. But after a certain point, there's no escaping. Every element in the sequence down the lane after a cutoff point will lie in this neighborhood. And so that means we are saying down the line the numbers in the sequence will start crowding 0 and will be in this neighborhood. and that's what this limit definition means. Now you can ask, well, what if somebody decides to change that neighborhood to something even tinier, like that? Then the answer is still you will be able to find a cutoff point. It won't be same as the one that suited the other interval. Maybe you have to go down even more down in the sequence, but you'll still reach a point where you will say, okay, now after this point, all the elements in the sequence are now very close and they crowd 0 and they're all entered in here. The first finite number of terms, maybe they're outside, but the rest of them are all in here. So as an example, if you were to choose this red interval as 0.001 units around 0, then you'll quickly notice 1, 1/2, 1/3, 1/10, 1/20th, they all lie outside of it. They're far away from 0 if 0.001 is what this distance is. And you'll see by the time you get to the 1000th term, that one barely, it's on that red dot, it doesn't quite make it. So, but after the first 1000 terms, or if you want to say maybe first 1005 terms, if you just want to be safe, you're not going to make any statement about the first 1005 terms in the sequence. But after that one, after that cutoff point, every element of the sequence after that cutoff point will make it into this tiny neighborhood of 0. So the game is, no matter how small of a neighborhood you pick, corresponding to that neighborhood, if we are able to find a cutoff point in the sequence and say everything that comes after that cutoff point in the sequence, if all of those numbers lie in here, then we say, yes, the limit of the sequence exists, and it is in fact that point where all of those numbers are crowding. So that ends the digging deeper part. Let's look at more examples where we still stay on the intuitive level, where we look at tables and where we just guess the limit of the sequence by looking at a pattern. So if the first example gave you an impression that perhaps we could just guess the limit of any sequence without any work, this one should challenge you a little more. Here, look at the sequence. 1 plus 1 over n to the n, the whole quantity to the n, that is the general nth term of the sequence. As you can see from here, we are not able to say as n gets bigger, as we start putting n equals 1, n equals 2, n equals 3, n equals 100, and so on, all of those numbers. What happens? On that one hand, you see 1 over n gets very small, but on the other hand, you're raising that number to a very large number. And just looking at it, it's not very clear what's happening to the pattern of of those numbers. So here, I suggest you create a table of values. N, that's the value of n, that is the natural numbers, n, and here 1 plus 1 over n over n. Remember, from our definition of sequences, n comes from the set of natural numbers, so you can only put in integer values, positive integer values, 1, 2, 3, 4, and so on. You don't have to begin with 1 because we're sort of doing this in an intuitive way. We're trying to guess the limit. So you can just look at n equals 10, n equals 20. This is really your choice, what you want to put in here. And they have to be positive integers. Corresponding to that, you can calculate 1 plus 1 over n to the n, and you fill in those numbers, and you will begin to see there's a pattern. And in fact, the answer is that the sequence approaches E, and we write it this way, limit, and here what I have is exactly this formula. N goes to infinity is telling you you're looking at the elements of the sequence down the lane, not the first few elements, what's happening as you put in larger and larger integer values of n. And the answer is E, and you can prove this using sophisticated calculus methods. Right now we are only doing things with intuition and using numerical methods. Another way of stating this answer is the sequence is convergent and it converges to E. This is pretty standard math language. It may sound a little unusual at the beginning, just this way of saying it converges to E. Remember, E is a number is a point on the number line. So practice this. And here's another example. Guess the limit of this sequence, n factorial over n to the n. Again, a reminder, n is coming from the set of natural numbers. So n is 1, 2, 3, 4, and so on. So, and for each value that you put, you get your elements of your sequence. Once again, create your table of values. Here you can pick 1, 2, 3, 4, 5, 6, the first few, and pretty soon you'll see a pattern. Pretty soon you'll see a limit of n factorial over n to the n as n approaches infinity is 0. So here too, this sequence is convergent and it actually converges to 0. Probably something you might not have guessed, because as you know, when you put in large values of n, then n factorial becomes really big. But so does n raised to the n. And so here now we don't have an intuition as we did for 1 over n, where we could simply without any work guess that the sequence 1 over n converges to 0. But here and here we don't have that kind of intuition. But a table like this helps you guess the limit